Hello everyone. Today we will be discussing about how to do analysis of pre-stressed concrete. So let us assume a particular beam which is pre-stressed and let's try to find out how to analyze this particular beam. So I have considered a problem. The problem statement is a rectangular concrete beam of cross section 30 cm deep and 20 cm wide is pre-stressed by means of 15 wires of 5 mm diameter located 6.5 cm from the bottom of the beam and 3 wires of diameter 5 mm 2.5 cm from the top. So we have a cross section of 200 by 300 where we have 15 numbers of wires or tendons which has individual diameter of 5 mm which is placed at a distance 65 mm from the bottom or from the soffit of the beam. Again we have another 3 tendons which are placed just below the top fiber of the beam at a distance of 25 mm. Now assuming the pre-stress in steel as 840 megapascal, calculate the stresses at the extreme fibers of the midspan section when the beam is supporting its own weight over the span of 6 meters. If a uniformly distributed load of 6 kN per meter is imposed, evaluate the maximum working stress in concrete. The density of concrete is given as 24 kilonewton per meter cube. Okay. So the problem statement, if we draw the cross section as well as the elevation of the beam from the problem statement, it will look like something like this too. Here, this is the section. Here we have the three numbers of tendons at the top and the 15 numbers of tendon at the bottom, having a distance of 25 mm and 65 mm from top and bottom fiber respectively, and the span of the beam is 6 meter which has a live load of 6 kilonewton per meter. Okay, and we also have to consider the dead load or the self weight of this beam. So let's go to the solution. So first of all, let's look at the data that are available. The width is 200 mm, this is represented by B. The depth is 300 mm. Length is 6 meters. Area of cross section, this is the gross area of cross section is B into D, that is 6 into 10 to the power 4 meter square. The second moment of area about the neutral axis is 4.5 into 10 to the power 8 mm to the power 4. Then find out the section modulus. As this is a rectangular section, so the section modulus will be same for both the top as well as the bottom section. So the section modulus Z can be find out I by Y. Y is the distance from left of the neutral axis, which is D by 2 here. So that is 3.3 into 10 to the power 6. As this is a purely rectangular section, so the section modulus for the top section as well as the bottom section will be same, which is equal to Z. Okay, so ZT is equal to Z and ZP is also equal to Z. Now at the bottom of the section there are 15 numbers of tendons having a diameter of 5 mm. This has been already mentioned in the problem. Now the area of the tendon at the bottom, so total area of tendons at the bottom is given by AT1 is equal to 15 into pi d square, that is phi 1 square by 4, which comes out to be 294.524 mm square. This is the area of tendons at the bottom. Okay, the total area of tendon at the top is 3 into pi d square, that is phi 2 square by 4, which comes out to be 58.905 mm square. Now what is the pre-stressing force that is given to us? That is 840 megapascal or Newton per mm square for each tendon. And then if this is a stress, what will be the total force of the pre-stressing force? Then P will be sigma into the total area of pre-stressing steel, so which is come out to be 296.881 kilonewton. Now let's go into the load calculation. So we have to consider the self weight. So density is already given, that is 24 kilonewton per meter cube. So the self weight per unit meter will be B into D into rho, which comes out to be 1.44 kilonewton per meter. And the moment due to self weight, so moment due to self weight is come out to be WL square by 8, which gives 6.48 kilonewton meter. As well as we also have live load, which is 6 kilonewton per meter, and correspondingly we can find out the moment due to the live load, which is 27 kilonewton meter. Now now we need to find out what is the distance of the centroid of this two sets of tendons that are placed in this section, because you can see there we have 3 tendons at the top and 15 tendons at the bottom. To find out the eccentricity, we just first need to know what is the centroid of this total 80 numbers of tendons. So for that, let's find out what is the distance of the centroid of these tendons from the base of the section, which is given by y is equal to 15 into what is the distance of these tendons from the base, that is 65 mm. So I will multiply 65 mm with that, then plus how many numbers of tendons are there at the top, we have 3. So 3 multiplied by what is the distance of these tendons from the base, this is 300 minus 25, okay, into divided by the total numbers, that is 15 plus 3, that is total 18. So if I do the calculation, you can find out what is the position of the centroid from the base of the section, which is 100 mm. So if this is y here, so if this is the centroid of this whole 18 numbers of tendons, then this location of this tendon or the centroid of the tendon is 100 mm from the base. Now as we have find out the centroid of the tendon, now you just assume that all these 18 tendons are clubbed together and just placed at this location. These all the tendons are clubbed together and placed at this location, because the effect of putting all these 18 tendons at this centroidal position will be same to the effect of this distributed position. Okay, so as this is a centroid, so we can find out what is the eccentricity. And what is the eccentricity? Eccentricity is the distance of the position of the tendons from the neutral axis of the section. So as we have a purely rectangular section, so its neutral axis will lie at a distance d by 2, that is 300 divided by 2, that is 150. And the distance, that is we need to find out the eccentricity, which will be 150 minus 100, that is 300 divided by 2 minus y, which is going to be d by 2 minus y, which is equal to 50 mm. So this is the eccentricity for this whole set of tendons, so 50 mm. Now the last portion is to find out the stresses, so stress calculation. So first of all, we have the pre-stressing force, which is given by P, right? What is our total pre-stressing force? The total pre-stressing force is 296.881 kilonewton, right? So total, what will be total pre-stressing stress in the concrete? This total pre-stressing force divided by the cross-section area, which is B into D, which is 6 into 10 to the power 4 mm square. So the stress in concrete, the direct stress due to pre-stress will be P by A, which is given by 4.948 Newton per mm square. So this is pure or direct stress. So the stress distribution will be rectangular like this, and this is compression, so it is positive. Now the bending stress that can develop due to pre-stress, because we have already discussed that if there is eccentricity along with the direct stress, there will be some bending stress. And we have also discussed that as the tendons are below the neutral axis, so due to this bending, the deflection will be in the upward direction. So at the top we will be having tension, at the bottom we will be having compression. Okay, and what is this stress value? That we can find out m by z, that is p into e. E is the eccentricity, that in turn will give you moment, p into e divided by z. Okay, so it will be 4.948 newton per mm square, and this value, as this is due to the moment, the stress will maximum at the top and the bottommost fiber, and it will vary in between. Okay, so as in the top we have tension, so it is negative 4.95, and at the bottom, as it is compression, so it is positive 4.95 newton per mm square. Remember one thing, I have only mentioned z. So as the section is rectangular, so as zt and zb, that is section modulus for the top and for the bottom, are same, that is why I'm only using z. If the section is not uniform, if it is a shape of, suppose, I having different length of the flange, in that case the section modulus for bottom section as well as the top section will be different. In that case you have to find out separately pe by zt and pe by zb, that you have to find out separately. Now bending stress due to self weight. So you know that self weight is going to act in downward direction. So at the top compression, at the bottom we will be getting the tension. So and what are the stresses? The stresses are the self moment divided by the z, that is 2.16, and the variation is like this. At the top we have compression, at the bottom we have tension. So it is 2.16 from positive to negative. Then bending stress due to live load, the similar diagram, and this value is going to come out to be 9 newton per mm square. Now you can see that we have four different components. One is for direct stress or pre-stress, one is direct stress due to one is direct stress due to pre-stress, one is bending stress due to pre-stress, one is bending stress due to self-weight, and the last one is bending stress due to live load. Now we need to combine all these stress diagrams. Okay, so if we combine it, so first is for these two are for pre-stress, this is for self-weight, this is for live load. At the top you can see for direct stress we have positive value, but for bending due to pre-stress the value is negative. So if I combine this, 4.95 minus 4.95 plus 2.16 plus 9, it will give you 11.16 newton per mm square. It's a positive value. That means the top you are going to get compression after combining all the effects, and at the bottom 4.96, which is positive, plus 4.95, which is positive, plus 4.95 minus 2.16 minus 9, which will give you 1.26. That means there will be a small amount of tension, that is the value having the value 1.26. So we can see that stress at the top, P by A minus P into E by ZT, because we are considering top, then plus moment due to self weight by ZT plus moment due to live load by ZT will be 11.16, as well as stress at the bottom is a negative value because we are having a tension at the bottom. So like this you can analyze a pre-stress structure. We have considered a rectangular section, but if it is a non-uniform section the process will be same, but you need to find out separately the ZB and ZT, that is modulus of section modulus for bottom as well as top, and also you need to find out the stresses at the top and bottom separately, and then you have to combine. So with this I would like to conclude today's class. Thank you.